I'm here to introduce you the next presenter, who is Mustapha Ndiballen. Ndiballen's background is on agriculture, mostly animal science. He had his master's degree in animal breeding from Ege University in Turkey. He also has a BSc in tropical agriculture from the National Pingtung University of Science and Technology, Taiwan, and a higher diploma in agriculture from Gambia College. He also did his high school in Amite Senior Secondary School. His professional experience is on animal production officer from the Department of Livestock Services, which is under the Ministry of Agriculture. His experience, head of ruminant unit, manage field demonstration scheme and training, support small ruminant production and composting initiatives. So basically this is about Mustapha Ndiballen, who is coming to present to you. I thank you.
It's morning, right, or afternoon? Okay, thank you so much, Abdullah, for that brief introduction. As he rightly mentioned, I am Mustapha Ndiballen, and I'm going to give you a detail of my presentation. Okay, in the first place, we were tasked to check the Mangrove Extent 2020 in the Gambia. So as we got here, we can see that the Mangrove Extent in 2020 in the Gambia was like 609 kilometers square, representing 88.90. The other aspect of it is the net change. So according to here, the net change in the Gambia has increased from 199.5 hectares between 1996 to 2020. And two notable areas were observed, that is the area around Banjul and in LRR. And according to the information, there was a notable positive change from like 1996 to 2009, if you can look at the graph. And also from 2010 to 2016, there was a steep decline that followed, which could be attributed to other natural or human activities. Then from 2017 to 2019, according to the graph, then there was a sign of recovery. So this recovery can be attributed also to conservation efforts or other natural or ecosystem recovery system. Then in 2020, there was a minor decrease which was observed, but less compared to 2019. Drivers of loss, as we or most of the presenters just saw us that in the Gambia, the main driver of loss in the Gambia here is erosion, as we can see from the graph, representing almost 79%. And these drivers of loss, like we were also tasked to check the mangrove loss since 2020 in the Gambia. And those alerts, as you can see here, there are two notable areas, as I just mentioned. One is the Banjul dryport, and the other one is in the LRR, which is the OMVG project, which is the main factor for the loss of these two particular areas. And the significant surge of alert was observed in April 2021. Okay, we are also tasked to check from the Global Mangrove Watch to see the carbon stock of the for the national level. And the carbon stock here, like we've seen that 58.16 metric ton carbon dioxide was observed in the Gambia for mangroves. And also the other question asks us to describe the mangrove impact in carbon sequestration. According to the photograph as you are seeing here, carbon sequestration is the process in which carbon dioxide is trapped from the atmosphere and stored into the soil or below the ground. And you can see why mangroves are more relevant than other ecosystems, because they are exceptional carbon storage capacity, they protection from carbon loss, they have long-term storage, and they have dual benefit, example, coastal protection, fisheries, biodiversity, etc. Again, the biomass and canopy height. So the biomass and canopy height in these two areas, the biomass is 54.8, and the canopy height in the Gambia is observed to be 8.21. And it is also mentioned that the ABG biomass density, as I just mentioned, most of these levels can be found in Central River region, North Bank, and Lower River region, characterized by tall mangrove stands, and they are ecologically important. So, suggesting that they support biodiversity, protecting coastlines, filtering water, and recycling nutrients. Okay, the other one is the restoration potential. The restoration potential score in the Gambia is 70, and the restorable means is 1%. So meaning that only 1% can be restored, but the potential is 70. So it also asks, describe the fishery pressure. So according to the picture here, the fishery pressure here is 376 days. As other presenters just mentioned, we have 365 days in a year, meaning that there is a lot of pressure mounted on fisheries, causing a lot of havoc or damage to most of these mangroves. And most of the notable areas here are Katong, Tanje, Banjul, and other coastal areas. So we are also asked to use the local area of interest. So here our local area of interest was the Tambi wetlands. And from here, in this area, the mangrove area for the selected area is 44.55 kilometers in 2020. And the alert here, it was, we have 62 alerts in that particular period, and the area selected, there was a decrease of 165.52 in this particular area, and which was the Banjul dryport. And the biomass and height of this selected area was 23.57, and the height was 5.3. Okay, we are also asked to generate a classifying Sentinel-2 mosaic in Sepal. So these were the steps used, and this was the first produced, and this was the classification. And the mangrove canopy height for this particular area also, as you can see, the height was 11.9, and the AGB was 144.43. So why global code? He said global code is simple, easily accessible, is a widely accepted formula, and relates mangrove height to biomass without needing local field data. So we move to the next one, which is optical remote sensing. So the question asks, what is the physical process behind optical remote sensing? So as we can see here, it says it works by capturing sunlight that has been reflected on the Earth's surface, as you can see from the picture. So when it touches the ground, it reacts with different objects or materials, like forest, water, grass, soil, and other materials, and each of them give a different way of reflection or absorption. So what is spectral signature? It's a spectral signature is a unique pattern of reflectance or absorption of electromagnetic radiation, that is light, by a surface or a material across a different wavelength, as we can see from the pictures here. So the other question asks, why do we see plants as green? Okay, healthy vegetation absorbs blue and red. and the green is reflected. So when the green is reflected, that is what our normal eyes can see from this picture here. So if the blue is reflected, so our eyes will see the green. This is why we can see plants as green. So the other question says, why do we need NDVI to detect healthy plants? So according to this graph here, we need NDVI to calculate to see the health status of the plant. So from the calculation here, we can see the NDVI for vegetation, soil, and water. So I took this from the graph, like 45 minus 10, using the formula that is near minus red all over near plus red. So from there, we can have our calculations. So what is the difference between optical and radar remote sensing? From the table here, we can see in vegetation we have excellent, limited, soil moisture poor, good, as it goes. Then the other one there, sunlight is passive and microwave there is active. Looking at the penetration of the clouds, here it says no, and there it can penetrate clouds. So that's just a brief comparison between the two. On that note, I thank you all for your kind attention.